Okay, welcome to another episode of Q&A about history of science and technology. And I'm happy to talk about both things that have happened in my lifetime that I have direct personal knowledge of and things that I might know from historical research that I've done. So there are a few questions that I see that have been saved up here from last time. 32 Bits of a Bus asked, any questions, any stories about your work for Thinking Machines Corporation? Well, sure, I can try and tell some stories about that. So first of all, what was Thinking Machines Corporation? It was a company based in Boston that made an early kind of massively parallel supercomputer-like thing in the early to mid 1980s. And I got involved with Thinking Machines. So Thinking Machines as a company was, its technical founder was a person called Danny Hillis, who had been a student of Marvin Minsky, who was a kind of AI pioneer at MIT, who I knew fairly well, who died a few years ago. Marvin had many ideas about the way that one could get things to think. And he had ideas about kind of the way brains worked. It's sort of funny because he started his career, Marvin did, back in the 1950s. He was a graduate student at Princeton. He did a math PhD there. But one of his earliest interests was in neural networks. Neural networks were pretty young at the time. The McCulloch and Pitts had kind of originally suggested kind of the sort of mathematical idealization of neural nets in the 1940s. And Marvin was interested in kind of applying mathematical methods to understand how neural nets worked. He also was kind of enough of a tinkerer that he had actually built physical pieces of electronics. I think he had a thing called the SNARC, if I remember correctly, which was a kind of a physical 1 or 2 neuron neural net thing. So he was very into that stuff. But then he kind of got very disenchanted with it after the 1950s, heading to the 1960s. He ended up writing a book called Perceptrons with Seymour Papert, which was kind of a mathematical analysis of particular kind of neural network, very simple neural network, and kind of showing that mathematically those neural networks were too trivial to do anything interesting. That became sort of a reason why people didn't use neural nets. Marvin, I think, was a little disappointed by that because his book was only about a very specific kind of neural net that didn't turn out to be the kind that ended up working in the whole sort of deep learning story that came much later. But in any case, Marvin then, this is what we're now talking about, prehistory of thinking machines. But Marvin in the late 50s, early 60s, got very interested in kind of the formal theory of computation, ended up writing an influential book called, I think, Computation in Finite and Infinite Machines, that was kind of a discussion of finite automata, Turing machines, other kinds of simple models of computation. Actually, as it happens, I literally just got that book down off my shelf last night because it's relevant to the history of a project that I'm working on right now that has to do with a person called Emil Post and these things called post-tag systems. And Marvin did some work on that in 1961. I could talk about that another time. But in any case, so Marvin got very involved in kind of this formal kind of analysis of computational systems, but then was involved in the startup of the AI lab at MIT in the early 60s when there was a lot of government funding for AI and so on, and got more into the kind of, well, how should we think about thinking in a more kind of holistic way, not in this kind of mathematical, very structured, very formal kind of way. And worked on all kinds of things and worked on all kinds of models for how thinking must work. And I think in the late years of his life, when I talked to Marvin, it's like, how should one think about how you're thinking about thinking, so to speak? And I think he viewed it more as a kind of some of his theories more as kind of meta theories in the sense of people like Freud than they were sort of mathematical theories in the sense of something like Turing. But in any case, there was sort of an intermediate period where he had these ideas about frames and this and that, and ways of sort of thinking about thinking. So one of his ideas was that sort of a key notion of thinking is about sort of having facts and making connections between them, that it's all kind of about that one can have a sort of meta theory of thinking that is about sort of the notion of representing knowledge and facts and thinking about facts as all about connections between things. So that was sort of a theory of AI. So one of Marvin's students, Danny Hillis, got interested in, well, what if we actually built a thing that implemented that theory? Could we make an AI by kind of setting up the system so that so that one actually had built in a machine something that implemented this kind of connection theory of how thinking might work. So that was beginning of the 1980s, and kind of the notion was, let's make it so that how would you make a machine that is all about making connections between things? Well, you need a machine that has lots of separate processors and where you're able to send information between these different processors. So that turned into this notion of, let's make this massively parallel machine that had lots of separate computer processors that are able to communicate with each other. Now, there have been a bunch of history to parallel machines. The most common kind of parallel machine was a single instruction, multiple data machine, where you were taking one set of computer instructions, is just feeding them out to this large number of different processors, which might have different pieces of data, like they might be analyzing different parts of an image or different pieces of some big graph or something, but they were all doing the same thing kind of in lockstep. And there have been a bunch of machines built for that purpose. One of the, well, let's see, there was one called the Iliac 4 built at University of Illinois. That was kind of one of the late stages of a kind of line of very distinguished computers built at University of Illinois, starting in the 1950s. And then there was another one called the MPP. What was that? The Massively Parallel Processor. I think that was a NASA project. There have been a variety of these kind of single instruction stream, many, all the separate data kinds of machines. The idea of the connection machine was something more ambitious. It was have all these processors, thousands and thousands of them, and be able to have separate operations go on in each processor. So the notion was, let's have 16,000, 64,000, processors, and let's connect them. And the sort of hardware connection was as a hypercube, a 16-dimensional hypercube, where each processor was connected in 16 dimensions, so to speak, or conceptually in 16 dimensions to other processors. But then the real sort of wonderful thing was supposed to be that you could take a piece of data at one processor and route it immediately to any other processor, so that you could sort of implement this idea of Marvin's of sort of connecting things together and representing things using these kinds of connections. Okay, so that was kind of the goal, and there was a question of sort of how would this actually get built? How would it get set up? Well, that quickly turned into, let's make special purpose processors that might be, each individual processor might not be able to do very much, but together they would somehow be able to do lots of big things. So I guess I got involved in this, when was it? I suppose Danny came to a conference that I organized at Los Alamos about cellular automata in 1983. And I think he was just starting to really work on thinking machines at that time. I somehow got involved as a consultant to the company. The CEO of the company was a woman called Cheryl Handler, who had previously done a company called Genetics Institute, which was kind of a sort of high intellectual value kind of scientists come in and build something that was of commercial value. She was sort of the organizer of the whole thing. They had a very charming, I always think startups work particularly well when they have a sort of an interesting kind of physical presence at the beginning. And they had rented a house, I think it was called the Thomas Paine House. It was a kind of a country house type thing in Waltham, Massachusetts. they'd rented this kind of sort of old house with grounds, and it had all wood paneling everywhere and all this kind of thing. It was wood paneling, and then there were cables snaked all over the place, and it was a very dynamic environment in which to have a startup. But in any case, they had also, particularly I think Cheryl had started recruiting sort of interesting characters to be involved with the company. Another interesting character who got recruited was Richard Feynman, Dick Feynman, physicist, who I knew quite well. His son, Carl Feynman, who had been a student at MIT and had kind of known the sort of gaggle of people, also started working there. In fact, Carl still works with Cheryl many, many years later in a different company. Carl had, I think, notably had insisted that his major at MIT will be philosophy, because that was something that Dick Feynman was like, oh, I don't believe in philosophy. Such is the way of children. But there were the Feynmans. Another person who was involved very early on, who just graduated from MIT, was Brewster Kahle, who's gone on to do the Internet Archive as well as several other companies. And with a bunch of different interesting people from different places sort of collected together for this company. Another person was a person called Dick Clayton, who'd worked at Digital Equipment Corporation as a hardware developer there. Back in those days, Digital was the world's second largest computer company, the largest being IBM. Digital Equipment was the second largest. They made the PDP series of computers, and then the virtual address instruction, the VAX computers. They were a very successful company. I was sad in recent times that their headquarters was in Maynard, Massachusetts. They were a company that, for various reasons, had these different. I suppose they had a distributed approach to work long before other people had distributed approach to work. But their distributed approach to work was to have these different facilities dotted around mostly Massachusetts and New Hampshire, I think. And their kind of particular feature was they had a fleet of helicopters that would take people between these different facilities, which was kind of exotic. But their headquarters was in Maynard, Massachusetts, in this converted mill in Maynard, Massachusetts, and they had a big factory in Maynard. And a few years ago, unfortunately, as Digital failed eventually as a company, they demolished this big factory. So that was kind of a sad thing to see. I do have to tell, I'm a little bit segueing from the original topic, but I do have to tell a story about Digital that was told to me by Ed Fredkin, actually, who's a longtime sort of fixture on the MIT and AI-ish scene, and also a long-term enthusiast of cellular automata. Ed tells many stories, some of which I've been able to verify. This is a story he told about Digital Equipment Corporation. One of the things that went really wrong with Digital was they didn't get involved in personal computers. And they have been involved in really, IBM had made these big mainframe computers. Digital came along and made what they called mini computers, which was still really physically huge, but they were a lot smaller and cheaper than the things that IBM was making. And that was how they got started in the PDP series of computers, and then up to the PDP-11 and so on, and then off to the VAX and such like. But when personal computers were coming in, there was a question, should they get involved? So apparently, oh my gosh, how can I have forgotten the name of the CEO? Oh dear. Well, anyway, their CEO at the time, who had been their CEO, my gosh, slipped my mind. In any case, in the Boston area, there had been Digital was a Boston-based company. Had Digital been sort of the long-term winner in the computer business, probably would have tipped the balance somewhat between East Coast and West Coast in terms of the energy around the computer business. I mean, Boston had originally been the site of Wang Labs, which had been the first word processing company, and that had sort of then Digital was sort of the next big Boston-based company. Anyway, the story, as told to me by Ed, is that at the key moment they were thinking at Digital whether they should get involved with personal computers or not. So they did a focus group, and they got a bunch of people, every day, people from all kinds of walks of life, and they said, what would you do with a personal computer? A personal computer is going to be useful. Are they a good thing? And apparently there was one teacher there who was one of the most enthusiastic people in the focus group, and who was talking about how wonderful personal computers would be, how important they'd be to everybody, et cetera, et cetera, et cetera. And the CEO of Digital was there listening to this and was sort of almost getting convinced, yes, these people are really enthusiastic, personal computers is going to be a great thing. And at the end of the focus group, this teacher was like, giving the speech about how wonderful personal computers were. And he just wanted to add one more thing at the end of the speech. And the one more thing that he added was, and I don't just mean here on Earth. And unfortunately, the claim was that was the moment at which the then CEO of Digital said, this personal computer thing, it's all nonsense. It's just a bunch of loonies talking about these things. Let's just stick to our main business of making mini computers and so on. And that was a bad business decision. But back to Thinking Machines Corporation. So Dick Clayton was sort of their hardware guy. He'd come from Digital. They kind of set about the task of building these this computer, and it was there were a lot of well, I was involved in this in various ways. I think I was not involved in any of things like hardware design and so on. I was somewhat involved in the architectural questions about how the computer would work. One of the key questions was, when you want to send a message from here to there, how would that work? And so it's like, we have a processor, it's at this coordinate in the 16-dimensional hypercube, it wants to send a message to this processor at this coordinate, what will happen? So they were very proud of the idea that you could just sort of give the message the relative coordinates of those different processors, and as the message sort of snaked its way through this hypercube, it would always sort of decrement the direction that it had gone in and say, I have less distance to go in that direction, et cetera, et cetera, et cetera, until it got to its destination. The problem was what happened when multiple messages wound up on the same processor. And how would that work? Because there was a certain buffer that allowed you to have a certain number of messages queued up. But if that buffer overflowed, then things would back up and messages wouldn't be able to get delivered there, and it would all be a big mess. So one of the questions that I did get somewhat involved in is this question about sort of what was the right algorithm for transmitting messages but from one processor to another. I hadn't been involved in the sort of original development of that, but later on, it seemed like there was a problem with this. Because one could do a calculation that said if you were routing messages around completely randomly, then things would be fine. Similarly, if you were routing messages around in the way that you would for some algorithms where there was a very structured exchange of information, like in drawing a fast Fourier transform or something like that, you'd be fine. But the question was, what would happen when it was more random? And it was a case where actually, I think Dick Feynman had got this argument based on statistical physics for why it was going to be okay to have a limited size of buffer on these various processors because messages wouldn't queue up too much. And there was a young graduate student who had run these simulations, and she was like, no, this isn't going to work. There's going to be this tail of message delivery. And it was like, well, Dick Feynman's worked out that there isn't going to be. And I was like, I think the simulation is more likely to be correct than this analytical, calculation. But well, as it turned out, it was sort of too late because these particular decisions had already been burnt into the hardware of the computer. And there were custom chips that had been built and so on. So it was kind of a too late type situation. But that turned out to be actually quite a problem in the end, that for many kinds of actual ways of routing messages around the computer, there was a sort of long tail of messages that hadn't yet been delivered because they got queued up and backed up in these kind of message traffic jams and so on inside the computer. But I would say that, let's see, in terms of the sort of origination of the company and so on, they, it's been a while, so I don't remember the complete exact history of the whole thing. But somehow I was involved in the discussion about the name of the company, and I don't remember exactly how this went down. But there had been a company that I'd known in England called Research Machines that I thought was a cool name for a company. That company still exists. It went into kind of educational computing and so on. Wasn't its origin, but somehow I was involved in either suggesting or supporting this idea of thinking machines as a name for this company that was building this kind of machine that was going to do this kind of AI thing. And that somehow got transmuted into international thinking machines was a possible name. And the concept was, just like IBM had originally been international business machines, that they would be sort of the international thinking machines. And that was kind of an aspiration in the IBM direction. It was also sort of amusing that Tom Watson at IBM was fond of having these signs up for his employees that said "think." And so the joke at Thinking Machines was, if it was called International Business Machines had these signs that said "think" put up for their employees. So International Thinking Machines would have a sign put up for its employees that said "business." It was an idea, never really got implemented. But in any case, then I suppose my biggest contribution probably to Thinking Machines Corporation was a day, I don't know when it was, probably can be looked up, when Danny and I I was in Boston and we went to see this movie together. It was a movie called War Games, which was kind of an early computer hacker movie about how a young, I think the actor was Matthew Broderick, sort of breaks into this computer that's the Strategic Air Command's computer and is about to start World War III. And there's a character in the movie actually who Ed Fredkin claims is based after him, who's some strange guy who lives on an island and has an autonomous pterodactyl and so on. But in any case, this movie. And but one of the sort of centerpieces of this movie is a computer. I think it's called the Whopper computer. That is a computer that's supposed to be the thing that controls the defense of the United States or whatever. And its big feature is it's covered in flashing lights. Okay, so we see this movie. We're walking out of this movie, and I kind of, for some reason, I still remember this moment. And I turn to Danny and I say, maybe your computer should have flashing lights. And well, turns out the connection machine computer, which is what Thinking Machines built, that was this big, it ended up having a lot of red flashing lights. Actually, the industrial design of the connection machine computer, it's a very nice industrial design. It looks a bit like, it's a cubical thing, it looks a bit like a Rubik's Cube, has these different sort of sub-cubical segments, kind of reflecting in some way its kind of hypercubic structure. There's a young designer, Tamiko Thiel, I think is her name, who was sort of a sculptor, artist type person who did the industrial design for the computer. And it was a very striking industrial design, a real, a big black cube. I mean, the thing stood about as tall as a person, as this big black cube. But the thing that really made it in the end was the fact that it was, that inside this big black cube, it was translucent plastic stuff on the outside, were a big array of red flashing lights. I think that was my contribution, so far as I know. And so so when a connection machine computer was running, covered with flashing lights, I have sometimes said that the connection machine was the world's most successful direct-to-museum computer, because if nothing else happened with it, even if it was not very successfully used as an actual computer, it's a wonderful museum piece. Actually, I have to say that, and so you'll find it in a lot of computer museums, et cetera, et cetera, et cetera. You also find it in movies. I think it was in Jurassic Park, among others. Exactly what it was doing there is not completely clear, but it was flashing its lights and having a good time, so to speak. I mean, I have to say, in a footnote to history, a longtime employee at our company ended up somehow getting a portion of a connection machine computer that was given to him by a US national lab that really wanted to get rid of it, and basically said, if you'll just take this away, you can have it. And so he had it for a long time in his garage, and I believe it is now at our offices in Illinois. I haven't seen it there, but so I believe we have a piece, I don't know what it is, a quarter of a connection machine. I'm afraid probably not. I don't know whether it's alive enough to have its lights flash. It's a good question. I haven't seen it in the flesh because there's been a pandemic and things, and I haven't been there, and I should check it out. But in any case, but back to the company. So let's see what oh gosh, it's a bit sorry. This is what happens when memories that are 35 years old or something, they tend to come back in a bit of a jumble. But about thinking machines. So the original development was all about making this black cube computer that would have, well, there was a small version with 16,000 processors and a big version with 65,000 processors. I think it was the basic price point was $1 million per computer. And the idea was to make this to implement Marvin's theory about AI and make this kind of this connection machine AI computer. That wasn't a great business strategy. I mean, it didn't take a lot of effort to point out that, who is going to be the single user AI researcher who is going to be given this $1 million thing to use. How is that going to work? Cheryl was very keen that the company really sell to companies that would have a practical sort of industrial use for the computer. And I think there were some finance companies, I think, if I remember, maybe American Express, maybe Dow Jones, they were early customers. There was clearly an opportunity at national labs, places like Los Alamos, Livermore, places like that, which were interested in having the fastest computers, both as a way of researching computers, but also they had a very specific use case for those fast computers, which was, particularly at that time, which was doing simulations of physical processes and particularly nuclear explosions. Again, I'm segueing slightly into a slightly different topic, but one of the things that happened at that time was the test ban, nuclear test ban. And it had been the case when you were trying to figure out if you could make a nuclear weapon that worked, you just tested it. And you either tested it by digging a hole in the ground and sticking your nuclear weapon in the ground and blowing it up, and then you'd have all these pictures of the sort of ground caving in on top as things had been vaporized underneath or something. Or in earlier years in the 1950s, particularly, there were nuclear tests in the atmosphere, particularly in the Pacific and so on, making a bit of a mess. I mean, it's sort of a remarkable thing that the nuclear tests in the Pacific caused. When I was a kid and you learned about hydrogen, you learned hydrogen has 3 isotopes that are sort of reasonably stable. The 1 proton, 0 neutrons, the deuterium, where there's a proton and 1 neutron, and tritium, where there's a proton and 2 neutrons. Well, tritium was not stable. It was radioactive with a half-life of maybe, 17 years or something like that. I kind of learnt the abundance of tritium in hydrogen, which was mostly based on abundance in seawater and so on, as a proxy for sort of the general abundance of tritium, was a number. Well, it turns out that number is now different. Why is the number now different? It's different because when I was a kid in the 1960s, the tritium, there was a bunch of tritium that existed in the world from nuclear explosions that had happened in the Pacific. And turns out water mixes very quickly on the Earth. And so the tritium was spread to water all over the Earth, and it affected the isotopic abundance. But anyway, back in the early 1980s, even underground testing of nuclear weapons had been banned. And so there was the question, how would one ever know what was going to happen if one wanted to change the design of a nuclear weapon or whatever else? How would one ever know it would work? Well, the answer is you had to do a computer simulation of it. That was a hard thing to do. And people tried very hard to validate that the simulations that they did would actually work. And it required sort of supercomputers and things to be able to do those simulations. One of the important validations was supernova explosions, because that was sort of the same physics of nuclear processes going on. And so there was a sort of a big trauma for a long time that supernova explosions, if you calculated them using the same general kind of code that was used to study nuclear weapons, that, gosh, supernovas shouldn't happen. Stars shouldn't explode. It's a bit of a problem. It turned out many years later, I think, I've heard this story in various variants, so I'm can't say it from completely first-hand experience, but my impression is that what actually happened was that some neutrino opacity data cards had been mistyped. So it's a big, complicated simulation, and turned out the amount of the rate at which energy could be lost from a star by neutrino emission was wrong, and that was because some data card had been mistyped, and that turned into this whole supernova can't explode thing. But in any case, at the time, big focus on supercomputers, partly for nuclear weapons simulation, so that was sort of a good potential market for the connection machine and for thinking machines. They were not so keen on that market, not because they were opposed to the defense establishment. In fact, they had a lot of close connections to the defense establishment, but because I think they were really interested to see sort of truly commercial, scalable applications rather than something which will be limited to a small number of government labs. But in any case, the government labs were a good market for them. So something that happened that I was deeply involved in, I tried to figure out, so what was a connection machine actually good for? I actually recently found my notes about sort of scientific computing with the connection machine, which I recently put up on the web. But one of the things that was sort of a big application area for supercomputers was fluid dynamics, was computing the motion of fluids, whether air or water or something else, according to the equations of hydrodynamics and so on. So I've been working a lot on cellular automata, discrete systems, very simple programs, what they did. And so one of the things that I sort of realized was, gosh, you could use this connection machine computer. It was a really good cellular automaton computer, even if that wasn't making use of its whole connection, connect this to that everywhere type capability, was really good as a cellular automaton computer. So let's use it to do fluid dynamics. Oh, and by the way, can I invent a scheme for fluid dynamics that would make use of cellular automata? So it turned out I did, and turned out that was started a whole area of fluid dynamics simulation, where instead of having sort of starting from the continuum equations and breaking them down to something a computer can deal with, you start from kind of these idealized discrete molecules and then kind of build up to something which simulates the fluid. And that idea actually, interestingly, has reappeared in what we're doing in our fundamental theory of physics now. And in fact, Jonathan Goraud, who's been working on that project, is even as we speak, working very hard on being able to have a new scheme for doing numerical relativity and computing black hole mergers and all those kinds of things, using a method that is not based on cellular automata. It's based on these hypergraph rewriting systems that we're doing right now, but it's using the same idea as this thing that I originally invented as a way to find something useful for the connection machine computer to do. So it's one of those cases where sort of technology development drove a piece of basic science. I also, I've been working, I actually worked on Rule 30 and my kind of randomness generation mechanism when I was working, a summer that I was working, I think summer of 1984, maybe 1985, I worked on that. And that was a case where, again, I was able to use the connection machine computer to do this very large scale calculation of the Rule 30 cellular automaton and try and validate the randomness that Rule 30 seemed to be generating. I remember one of the things, I think I have it somewhere, I was able to make this giant printout of Rule 30 that was printed out on the same printer that the hardware designers at Thinking Machines used to print circuit boards and so on, and chip designs and such like. But anyway, was a nice kind of visual, which unfortunately I don't think anybody took a picture of. It would have been one of these good historical pictures, I suppose, where they had this giant printout of Rule 30 unrolled on the floor at Thinking Machines, and all kinds of people, including myself and Dick Feynman, were kind of crawling over this thing with meter rules, trying to measure various properties of this particular thing. And Dick Feynman had this whole argument about why some particular angle, some particular thing should be 0.25. And it turned out upon more detailed measurement, it turns out to be 0.2481. But 0.25 is a good approximation, but we didn't understand why it wouldn't be exactly 0.25 based on that calculation. But I remember in one of the things which for me is a kind of an interesting story. I mean, after that sort of adventure of the meter rules and Rule 30 and so on, Dick Feynman had been looking at this Rule 30 thing of mine and was like, it's at first he was like, I can't believe a system rule that's this simple can produce this much complexity. And eventually he's like, okay, I agree, it does do that. There's no kind of way to sort of crack it and find out that it's actually simpler than that. But right at that moment when we were sort of studying this big printout, he kind of takes me aside and says, look, I just want to know one thing. How did you know that this particular simple rule was going to produce all this randomness and complicated behavior? And I was like, well, I didn't. I just did a bunch of simulations and, I did these experiments and this is one of the things I found. And so he says, I feel much better. I thought you actually had some intuition that would tell you that this is how it had to work. And I said, no, it's just experiments, just an empirical science kind of thing. Okay, he's much happier with that because his intuition, like mine, didn't encompass this kind of phenomenon. It was very surprising. And, I think he was, Dick Feynman was always a person who was very keen on kind of sort of adding intuition into physics. I mean, he tended to work in sort of the inverse of ways that some people, including myself, probably tend to work, which is he was a calculator first and intuition later kind of person. So he was very good at calculation. He was very good at actually working things out, usually using not terribly high-tech mathematics. He usually used sort of 19th century mathematics, kind of calculus plus type mathematics. But he was very good at that. And, he would do these long calculations. And the big surprise for me is he would get the right answer. And, I think to get the right answer, you have to know, well, I can approximate this, I can drop that. I need to, if this isn't coming out right, I must have made a sign error somewhere, et cetera, et cetera, et cetera. You get the right answer. But he thought that was trivial, getting the right answer from these calculations. So he would take the result of the calculation and he would try and think, is there an intuitive way to see why it's obvious that this will be the answer from the calculation? And then he would eventually, usually, come up with this amazing sort of intuition-based explanation of why it had to be that way. And then he wasn't very impressed with the fact that he'd done this big calculation, got the right answer. He'd throw that away. And he'd just tell people, well, the answer is this because, and then he'd explain this piece of intuition. And so it was kind of funny because people would, I would sometimes know about what the backroom calculations were. And it's like people would be like, oh, that's a very impressive piece of intuition. And then they would try and work out, how would we calculate that? Because we don't have this kind of intuition. How would we calculate that? And sometimes it took years for people to try and reverse engineer what calculation would give you the same result as this intuition. But Dick Feynman already had done the calculation. He just didn't tell anybody about it. And I don't think he did that to be kind of a better showman. I think he did that because, as is often the case, the calculations came easily to him. And so he didn't think they were anything remarkable. The intuition, hard for everybody. It was hard for him too. And so that was much more something he felt, proud of and impressed by, rather than just, oh, it's just a calculation kind of thing. Anyway, thinking machines. Well, so, I would always be jumping up and down about how, the business strategy of the company wasn't the right thing, et cetera, et cetera, et cetera. And Dick Feynman would always say, we often timed our visits there to coincide. He would say, let's just hide away and do physics. Let's, leave these guys to run their business. We don't know anything about running businesses. Let them run their business. We'll just hide away and do physics. And I was like, but it's going to fail. It's you can't do that. It's you've got to think about what the market is, what how to actually make a thing where the product you're selling is actually something people want to buy, and so on. But anyway, it's I think Dick Feynman's experience with sort of business and business management and so on hadn't been particularly positive. I mean, the two groups that he had most interacted with were university administrators and publishing companies. And he was very down on both of those groups. And probably those haven't attracted the sort of the most, at least, these industries go up and down, but I think particularly at that time, they weren't attracting the sort of perhaps the best and the brightest in terms of strategic business thinking, more people who were, running an organization that already existed and so on. And so I remember Dick Feynman wrote a book called QED about quantum electrodynamics. And I remember him just railing on and on to me about these publishers. They're so stupid. They're putting this cover picture on this book, and it's nothing to do with quantum electrodynamics. And I keep on telling them, it was a picture of some Newton's fringes in some oil type thing. And he's like, this doesn't need quantum electrodynamics. This is just classical optics. It's irrelevant. They don't understand, et cetera, et cetera, et cetera. But in any case, so that was kind of the background to that. I think also, one of the early investors in thinking machines had been William Paley, who was, William Paley, or am I mistaking that with the early natural theology person? In any case, the person who was the relevant person in this case is the founder of CBS television network, who was a relative of Cheryl Handler's, actually. Anyway, he was one of the early investors in Thinking Machines Corporation. And I think one of the claims that one of the things he said was, look, I'm going to invest in this company. And if this company has a 1 in a million chance of inventing the transistor of artificial intelligence, this is a huge win. I have to say, the cynical me said when I heard that, I said, I wonder how long it will be before, he's kind of banging his fist on the table saying, where's the revenue? I think the answer was, well, maybe a couple of years. But in any case, I think that such is the way of kind of I don't know, investment or something. I mean, I think it's Thinking Machines was intended as a serious commercial enterprise. In the end, well, one of the problems that they had was, it's sort of an interesting product design issue, was their machine a generic supercomputer, or was it this special wacky thing that was this experiment in making a massive number of processors that worked in a way that was very different from other computers? The primary competitors at the time were Cray computers, Cray supercomputers, and Cray computers basically were running Fortran programs. They were taking floating point numbers, they were crunching them, they had array arithmetic, they had all kinds of things like that. And the connection machine didn't have any of that. It just had processors that operated with 4 bits at a time. Didn't have any notion of real numbers. It didn't have any notion of floating point, all these kinds of things. So it was, it was great for cellular automata. It was terrible for standard floating point arithmetic. And for example, in doing fluid dynamics, there was this choice. You could either use my kind of method with cellular automata, where just working up from the bits was great, or you could use the traditional method doing numerical analysis with the Navier-Stokes equations, in which case you had to work with floating point numbers. You had to work kind of down from the continuum. So it was, in a sense, it was, and particularly there was one marketing guy named Jim Bailey, who was at Thinking Machines, who kind of got this point very clearly. It's like, if cellular automata wins, then, in fluid dynamics, then the connection machine wins. If Navier-Stokes wins, then Cray wins. And so it was kind of a science and technology kind of going hand in hand, and quite a bit of progress was made. But the problem was, when it came to being out in the field, actually selling a machine. If you're a salesperson for a $10 million supercomputer, for example, you might sell one every few years, and you want to kind of have the best shot. And it got very complicated to do the selling of this machine, where the competitor was the Cray computer, and it was like, well, where's your Fortran benchmark connection machine? Well, we don't have a Fortran benchmark. Well, why don't you have a Fortran benchmark? Are you slower than Cray, or what's the story? And so that was a big confusion. And I think the wrong decision was made. I think the correct decision, which I certainly pushed very hard, was, this is a different data point in the world of computers. It's relevant for people who care about the future. It's not relevant for people who just want to make a continuous gradation from the past. But unfortunately, sort of market forces and the sort of sales operation and so on ended up with, oh, let's add a floating point unit. Let's make something that's kind of a bit like a Cray. That was not a good idea. And I think in the end, the company failed, and was most of its pieces were sold to Sun Microsystems in the end, which in turn eventually got sold to Oracle. But in any case, I suppose one other piece of the whole story It's a long and shaggy story, isn't it? I mean, this is what happens after I've interacted with this company for quite a number of years. Another piece was the design of languages. So the connection machine computer, sort of the primary sort of control computers were Lisp machines, which was kind of interesting. And so there was a variant of Lisp that was intended to run on this parallel computer. I have to say, I never really used this much. It was used a bunch to do calculations sort of for me, but I should have gotten my hands more, my fingers more on the keyboard there of really using it, because I really didn't. And it was a little bit of a babysitting required kind of thing, and you had to actually be at the level of understanding the details of the hardware to really write these programs. Actually, one of the favorite things, which I don't think I unfortunately kept, which happened, which was just a classic, was we're doing these fluid dynamics simulations on the connection machine computer. They're literal calculations where there are molecules that are represented by different processors on the computer and so on. One of the processors actually physically blew up, exploded, whatever, failed, green smoke came out of it. What one saw on the Lisp machine that was sort of watching that simulation was this giant fluid velocity right there at that region in the fluid, because there was actually a mapping between the physical location of parts of the fluid and physical processes on the connection machine. So explosion in processor means giant, fast fluid flow there in the picture from the machine. But anyway, so one of the things that I worked on was developing an extension to C for the connection machine. C star was the name I gave it, which was intended to be a kind of extension to C that would be good for a parallel computer. And I was very proud of the fact that it was a very minimal design. In the end, there was just a single new keyword, which was the word parallel. And so in C, you can declare something like int x means a variable x of type integer, or int star x, a variable that is a pointer to an integer. And so the idea was there will be a parallel int x, which meant there was going to be an instance of x in every processor of the connection machine. And then the idea was that star x, which would take the address of something which stored an integer, star x, that indirection operation, would be the thing that actually caused it to move data from one processor to another. So if x was a pointer to an integer, it might be a pointer that represented a location on different, this keyword parallel was what I guess in C will be called a storage class. So I don't know whether it exists in modern versions of C, but it used to be the case that you could declare variables as being like register int blah, 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 which meant hint to the compiler. This variable is going to be used a lot. Try and put it in a register right on the CPU. So that was a kind of a storage class declaration. And so the idea was to add a parallel storage class declaration that would put it in all the different processes of the connection machine. Unfortunately, the implementation of C star got all tangled up, and it rapidly became this vastly more complicated thing. I don't know whether it was ever fully implemented at all, but I was sad because it was a very beautifully minimal design. And I think it was one of these cases where it just looked too simple. People couldn't believe that something that simple would work, but I think it would have done. Actually, at the time, I got quite interested in the problem of how would you really think about doing computation in parallel and doing lots of operations where you didn't necessarily know when the operations would occur. And I started thinking about using graph-based languages, doing graph rewriting as a way to represent parallel computations. That was in the mid-1980s. Well, ironically enough, graph rewriting is exactly the foundation of what we've been doing in our fundamental theory of physics. And by the way, from what I've learned from the fundamental theory of physics, I've now realized that finally, I think I'm beginning to understand how one can actually think about doing parallel computation using graph rewriting, using ideas that I don't feel so bad, because they're ideas I really profoundly didn't have in the 1980s. They're ideas that come from understanding this correspondence between graph rewriting and physics, and ideas about kind of programming in reference frames and things that one gets from the general theory of relativity in physics that one can now convert into things about graphs. And so I don't feel as bad that I didn't figure that out in the 1980s. But that was something that I had been thinking about at that time. When thinking machines finally kind of self-destructed, when was that? Must have been late 80s, early 90s. It was kind of a sad thing to see. I was not really involved at all at that time. Um, it had just collected a wonderful group of people who kind of scattered to different places and have had a lot of different interesting careers. The actual company, I think, could have been saved, I believe. I don't know the innards of it in probably enough detail to say for sure, but I think at the end, people just sort of gave up. I think that there'd been this push into doing something that was very unique and innovative, and there was a sort of pushback from the market, just do something generic. There was a certain tension between, the Cheryl used to have this sign up that was a quote from Danny that was something like, our mission is to make a computer that can be proud of us. And that's amusing, but in the end, there's a certain drumbeat of you have to actually sell computers to customers. I do also another thing that has to be said in terms of kind of the atmosphere of innovation, I would say, was very good at Thinking Machines. Cheryl had this kind of idea that in addition to getting sort of the best people, she wanted sort of the best office space, and she had a very interior designed, walls painted all different colors, and sometimes a little bit impractical of not having them be rectilinear, wall assemblies, so to speak, and that's always difficult to deal with. But she was very big on kind of the kind of providing an interesting and innovative environment, both in terms of people and in terms of the physical environment. One of the things that people used to kind of make fun of her about was when they first shipped connection machine computers, she had this whole team of people gift wrap. I'm not sure if it was the whole computer, if it was just the documentation for delivery to customers. I always thought that was cute. Other people thought that was Cheryl being crazy, but I thought that was a good way to present kind of the fact of being proud of the computer one had made, even if the computer couldn't yet be proud of one back. All right, very long answer to that question. Let me keep going here. Richard is commenting that C and C++ have a parallel for loop parallelization, but there's nothing for distributed variable storage. Okay, interesting. Okay, so we're still not at that level of modernness. Let's see, a few other comments here. Parmenides is asking about combinator graph reduction machines. I believe made by people like David Turner. I'm aware of these. Actually, a friend of mine from high school named Philip Gladstone, when he was in Cambridge, was involved in making one of those machines. I think it's based on microcode and so on. I've never touched one with my own fingers, so to speak. But yes, I'm aware of their existence. David here is asking, have I read Surely You're Joking, Mr. Feynman, and What Do You Care What Other People Think, and Tuva or Bust? I have to admit, I have not read these books. I have the theory that I've heard every story in them, sometimes in multiple variants. So I'm going to stick with the versions of the stories that I remember, so to speak, and not be spoiled by Ralph Layton's rendering of them in the books. But I think it was kind of interesting to see, Dick Feynman liked telling stories about things. I guess I do too. And sometimes, and I think one of the things to, somehow the stories Dick Feynman would tell would often be the same stories. And I think it's kind of a lesson for those of us who tell stories. It's like make sure you know the facts very accurately. And I've kept good archives. So when I consult those, I'm always kind of like, well, I had that more or less right, but there's a detail I didn't quite have right. And the detail doesn't usually matter to the arc of the story, but if you're doing history, those things can matter. I think that, I do think sometimes the title, What Do You Care What Other People Think, is a slightly amusing title for Dick Feynman because he did care a bit what other people think. I mean, he wasn't, he felt an obligation to his audiences, for example, when he would give talks. I remember one time, he was giving some talk and he was like, I'm worrying about this talk. And I'm like, why are you worrying about this talk? And he's like, because people think I give great talks. So that means that the threshold is raised. But yeah, I don't know. I mean, the Tuva story is also a story of Carl Feynman. And I do remember hearing all about Tuva long before the kind of the expedition to Tuva or whatever eventually happened with Tuva. I mean, I think it was one of these, let's pick the most obscure place in the world and figure out a way to it. I have to say that reminds me of a thing that I had going for a while with Danny Hillis, which was a crazy idea of mine back in the days when back in the days when you could just go to an airport and go get on a plane. There used to be this, when I lived in Princeton back in the early 80s, there was an airline called People Express, which was one of the early discount airlines. And it had the feature that you could like just go to the airport, get on the plane, you're going to wherever and go, pay for your ticket on the plane. And it's kind of like a bus, more like a bus type thing. So I had this idea a few times just as a weird thing to do in my last time I took a vacation, which was sometime in the early 1980s. It's like just go to the airport and go to whatever the first place that's listed on the departures for People Express, go get on that plane and go to wherever. And so I did that a few times. It's kind of interesting, younger, crazier time. But so I kind of had this thing that I had been thinking about doing with Danny, where we'd pick a random coordinates on the surface of the Earth. And it was sort of a competition. Whoever could get to that place first kind of wins the game. And, you just pick anywhere on the Earth. Well, we never implemented this. I thought it would be an amusing thing. I suppose it's a little bit like the modern geocaching idea or something, but, probably just as well we didn't implement it because those places, if they'd been, might have been in some awkward, dangerous, difficult parts of the world, and probably just as well we never tried doing it. Let's see. Right, Grateful Tomato comments that nowadays every modern computer has a connection machine in the form of a GPU. Yeah, kind of, although GPUs are very much, operating kind of in lockstep. There's, single instruction, multiple data type things where you say, this is a vector, I'm going to do this to it, rather than this idea, which was sort of the core idea of the connection machine, which was from any place to any place. Have this whole big shuffle around of all this data. That was the kind of idea. Let's see. Okay, let's see. Parmenides comments that, of course, I know the person. Yes, I consider Bruce Tickale a good friend, the person who started the Internet Archive. He has had an interesting kind of trajectory because he was at Thinking Machines after he was at MIT. And then at Thinking Machines, he developed this thing called WAIS, W-A-I-S, which was kind of an early sort of web-like thing. Let's see, he ended up selling WAIS to, I think, AOL. Actually, I have to tell another Thinking Machines story. So Thinking Machines did all kinds of research that wasn't specifically around its sort of supercomputer thing. One of the pieces of research it did was into early travel directions. So the idea was today, GPSs, all that kind of thing, it can tell you how to go from here to there. Okay, so back in the day, Thinking Machines, this is probably 1984, wanted to build a thing like that. So they had a street map, and they had been interested in routing algorithms where you could do the sort of computation, which could be done rather nicely in parallel, of how you route through the graph of streets to get from here to there. Okay, so what were you going to do back in 1984 to have people in practice use street routing like that? Okay, they had the following idea. take payphones. Okay, nobody knows what a payphone is anymore. Used to be the case that it was a common thing to, like, you didn't have cell phones, right? So if you were in some random place and you wanted to make a phone call, you would go find a payphone, pick it up and put money in it, or use your telephone credit card or something like that and make a call. Okay, so I guess at that time there was, caller ID was just coming in. These ANI data, the ANI data that represents the incoming call information was just coming in at that time. So you could get the incoming call information. What was the number of the cell phone you were calling from? So what they did was they got, for the Boston area, they got a directory of all the, I said cell phone, I meant payphone. What was what were all the payphones in the Boston area? What were their physical locations and what were their phone numbers? And so then the idea was to navigate, you would go and you would say, I'm lost. So then you would stop at a payphone, you pick up the payphone, you'd call the system, and the system would know where you were because it could see the caller ID information from this payphone. And then it would figure out where you were on the map, and then it had a voice synthesizer. It was using a thing called the Deck Talk, which was an early voice synthesizer. It was a kind of a weird product built by Digital Equipment Corporation. It's kind of this box about so big or something, of maybe a foot long or something. I used to have one of these, actually. I'm not sure what happened to my Deck Talk, but the Deck Talk was a voice synthesizer. So you would feed in, it was like a printer. You would kind of feed it, or more like a teletype. You would, a terminal, you would feed it text and it would say the text. And it had maybe 3 voices or something. It was a piece of hardware basically that did that. So they'd connected a Deck Talk to the phone. So you would, from the payphone, you would call into this number that you remembered that was their sort of direction information number. It would know where you were from the payphone caller ID, and then it would figure out, quickly what was the right route to where you were trying to get to, and then it would read you back the directions. Okay, so they wanted to test this. They had a version of this. They wanted to test it. So I said, sure, I'm an out-of-town person, and I'll test this thing. Okay, so there I was. It was actually one of the big mistakes was I should have had a co-pilot who actually knew the area at least a bit, and I should have also had a paper map. But anyway, I said, I'm going to test this. Okay, so there's some destination was picked, and I'm like driving around in some, I forget, it was probably my own car I had up in Boston. So I'm driving around and I got absolutely irreducibly lost. And I was calling all these different, stopping at all these payphones. And I don't think I'm very good at the best of times at hearing directions and being able to implement them. But this was the pits. And it was, I started in probably the early afternoon, and I remember it was getting dark, and it was, like, where the heck am I? And I don't actually remember how that resolved. Maybe I stopped at a gas station and bought a map. But that was so I got to be the very first human guinea pig for direction assistance on computers. And it didn't work well with me, but I was probably a bad case. I'm just the person who just follows the turn-by-turn instructions from the GPS. But it was an interesting, it was one of a number of very interesting initiatives. There was also a person called Dave Waltz at Thinking Machines who was involved in doing, they were doing text retrieval. And what was the idea there? They had was it a thesaurus, or what was the idea? But anyway, it was a kind of a whole text retrieval play that I think laid the groundwork for some of the things that ended up happening with search engines later on. But anyway, Brewster did this waste thing that sort of spun out a bit from Thinking Machines. Then after he sold that company, he did another company called Alexa Internet. Notice the coincidence of names is not as much of a coincidence as you might think. Alexa Internet had the idea of giving people a browser plugin that would give them some additional internet surfing capabilities, but also record what sites people were visiting as a way to know how many times different sites were being visited. And that's turned into the whole Alexa ranking mechanism that exists for websites. But anyway, Brewster sold that company in the end to Amazon. I'm pretty sure there's a straight line. I never actually asked anybody, I should have done, whether there's a straight line from the Alexa company that they bought from Brewster and the Alexa intelligent assistant that they use our technology, for example, for in that space. But anyway, so then Brewster sold that to Amazon and then started the Internet Archive with the money he'd made from that, and really kind of wanted to theme himself as the librarian of the internet, which I thought was just a terrific thing to do, and a terrific. I think Brewster's had a very interesting and productive career, and he's kind of gone through these multiple stages of very different kinds of things, and very interesting things being done at the Internet Archive and so on. I mean, I could, Brewster. I think it's fair to tell a few stories about Brewster. One of the things, he has the headquarters of the Internet Archive is right near the Presidio in San Francisco. And Brewster said to me one day, he had this logo for the Internet Archive, which was this kind of very establishment-looking, pillars and like the kind of icon that universities will often have, or courts of law will have, things like that, where it's the kind of the very classical building kind of temple-like thing. Okay, so he'd had this logo for a while. And then turns out there was a building just near the Presidio that came available for sale. And the building, as Brewster put it, looked just like his logo. So he had to buy this building. The building was a former church. What was it? Universalist church? I don't know. Some sort of intellectually oriented church sect. I don't remember exactly which one. But in any case, so Brewster bought a church, and that's the headquarters of the Internet Archive. And so the kind of the biggest room he has there is this this whole thing with a bunch of pews and so on in it, and with an organ, I think, even at the back. And so what did Brewster put in the pews? He's put these paper mache models of people who have been his long-term employees. And it's kind of Brewster's version of the Xi'an terracotta warriors. And it's really quite a strange thing to see. And I was last there maybe 18 months, a couple of years ago. I insisted on taking a picture of Brewster sitting with his paper mache model in the pews in his church. And actually, what's kind of particularly interesting about that sort of big sort of church room is that at the back of it are these things with flashing lights, actually, that are pieces of the Internet Archive. And Brewster's done this kind of surprising thing of being able to have air-cooled, very, very simple cooling mechanisms for his systems, and he's got the petabytes of data, and some of them are right at the back of this big room, sort of being cooled by just the volume of air in the room. I think Brewster's ended up with some interesting issues. They've been digitizing books. I guess he's now got 2 or 3 million books that are sitting in containers in the port of San Francisco, last I knew, that are a very big supply of mostly out of copyright books. And Brewster's been thinking about interesting plans for what to do with a few million books, given that they've mostly been digitized by now. They've developed actually, I made use of a bunch of early Brewster ideas because I wanted to digitize a bunch of documents that I have, and so Brewster was like, "Don't use a scanner, just use a camera. Just just press the button on a camera, high resolution camera works much better than a scanner once you built the kind of rig to have the camera look down on the document and so on." And I think we maybe suggested a few things that had to do with how to arrange for white balance and so on, and photograph additional things in the frame so that you can then do subsequent correction of colors and things like that. But anyway, that's boy, I can get into an infinite number of weird and funky stories. Question from Grateful Tomato here. what were the actual use cases of the interconnections in the connection machine computer. Good question. They were not as useful as you would think. So there were some things with routing and making and graph theoretical algorithms where you could make use of these, you essentially represent the graph in the connections. There were also things where there were a pattern of data flow that wasn't like in a cellular automaton where you just got local data flowing to neighboring nodes. There were things like doing fast Fourier transforms where you have this kind of butterfly arrangement of data being this shuffle network, kind of perfect shuffle like with cards network that is the thing that's good for fast Fourier transforms. And then there were some other cases. I mean, I think things like the problem of routing through roads and so on, I think that can be done in a way that works using that kind of parallel system. I mean, I don't think that many algorithms perhaps have been studied in as much detail as they could have been in the context of such an architecture, because it hasn't become a standard architecture. So people are much more, what can you do with vectors and arrays and so on, than what can you do with this very fast arbitrary connection kind of network. And I think, this problem of the delivery times is a serious problem. And it's known that, for example, I think Les Valiant had proved some theorem that said that if every piece of data gets routed to a random location and then to where it's finally going, it will never get gummed up. But then you're wasting all the time getting it to the random location before you get it to the final location. And many of these issues about sort of routing and how you do, I mean, these issues have come up in many kind of computer networking settings, but this is a much more extreme version of them than is typical for typical computer networks. I mean, I think the same thing came up again recently, a kind of a blockchain-like initiative called NKN, which I like because it kind of rhymes with NKS. It stands for new kind of network that kind of alliterates with new kind of science, and intentionally so. That's a sort of a way of routing messages through kind of an overlay on top of the internet, where it's sort of the routing channels are defined by people getting cryptocurrency for routing through their part of the network and so on. But they have some of the same kinds of issues that of delivery that I had seen with the connection machine, although I think distributed hash tables and things like that have a different kind of solution to these approaches. Well, I should probably wrap up because I think I'm about to run into the time when I'm supposed to go and do a piece of my day job. I noticed some questions here about the path of mechanics from Newton through D'Alembert to Lagrange. I could talk about that another time. Yeah, we seem to have talked a lot about Thinking Machines Corporation and the connection machine computer. It's a fine historical topic. I think probably should leave it there. So thanks very much. And our schedule is I will be doing another one of these history of science and technology Q&As. Plan is 2 weeks from today. Next week at this time, I'll talk about business and innovation. And then I guess on Friday, I'm doing a Q&A, general Q&A about science and technology for kids and others. So thanks for joining me here. And